Well, if you like science fiction and space travel, then this is, again, a fun section of any physics book. In particular, I'm keyed to Young and Freedman's University Physics, Chapter 12. This is the second section on weight. So how much do you weigh on other planets? How is it that we technically weigh what we weigh on Earth, remembering that weight is different from mass? Well, what is weight? Young and Freedman define weight as the weight of a body is the total gravitational force that is exerted on the body by all the other bodies of the universe. Remember that gravity, every body in the universe exerts gravity on every other body in the universe. But for all intents and purposes, we can just focus on, say, the Earth when we're talking about how much we weigh on Earth, because all the other the gravitational pull of every other body is fairly negligible compared to the gravity of the Earth. Well, we take Newton's formula, force equals G times m1 m2 all over r squared. And when we consider in terms of weight is the force of gravity on me, say. It's going to be the gravitational constant times the mass of the Earth times my mass, all divided by the radius of the Earth squared if I'm on the surface of the Earth. And by the way, remember from earlier sections that weight equals mass times the gravitational acceleration. Force equals ma, so weight equals m times the acceleration, 9.8 meters per second. And so this is kind of an overall view of the factors involved in the force and the acceleration, near the surface of the Earth. We can actually use this to solve, if we have the radius of the Earth, if we know what the radius of the Earth is, and we do, it's 6.38 times 10 to the 6th meters, then we can solve for the mass of the Earth. And the mass of the Earth turns out to be roughly around 6 times 10 to the 24th kilograms, which is heavier than me. But anyway, so one interesting thing to note is that if you solve for G, that is, if you solve for gravitational acceleration. So let's look at this part of the equation. mg and then the force using Newton's law of gravitation. If we solve for G, so let's divide both sides of this equation by the mass. Let's divide both sides by the mass. What's going to happen? These two are going to disappear. And so we're left with G, the gravitational acceleration, is equal to the big G, gravitational constant, times the mass of the Earth divided by the radius of the Earth squared. What we notice here is that the actual mass of me, or of anything, is irrelevant to the gravitational force, or the gravitational acceleration, or the acceleration to the gravity. This is what we've been saying all along, isn't it? That if you drop a train out of a plane, and you drop a Ken out of a plane, they're both going to fall or accelerate at the same rate as they fall. Why? Because the mass of the body itself turns out to be irrelevant to the gravitational acceleration. This is the old Galileo dropping two things off the Leaning Tower of Pisa and finding that they both fall at the same acceleration. And so we can now see why. Because the mass of the object in question is irrelevant when figuring out what the acceleration due to gravity is. Anyway, interesting. So, what if we want to know how much I weigh on a plane? Or what if I want to know how much somebody's going to weigh in the International Space Station? All we have to do is generalize the formula. So instead of using the radius of the Earth, we now use the radius from the center of the Earth. So if you're up in a plane, you're up maybe 30,000 feet. So we're going to add that 30,000 feet, to the radius of the Earth when we figure the r squared. And now we can figure out how much we weigh less on a plane or less at the International Space Station. As it turns out, we don't weigh that much less on a plane. It's not very great that we weigh less. I don't notice it when I'm on a plane. We can actually go beyond this, and what is the weight going to be above any planet or any spherical body? There's a problem. The example in this section of Young and Freedman has to do with how much a spacecraft would weigh on the surface of Mars or up going around Mars. And so we basically take the same formula. Instead of the mass of the Earth, we put in the mass of whatever body, I used a B, the mass of whatever body, we're talking about. So we could put the mass of Mars. We could do MM for Mars, or MS for Saturn, or so forth. There's a little question at the end of this section having to do with whether the escape velocity, would be actually it's a future section, whether the escape velocity would be different on a planet where the acceleration due to gravity is the same. And they use Saturn as an example. So you can look at Saturn in a later part of the chapter. Sorry. Anyway, so basically you just take the mass of whatever body you're talking about and substitute it in, and you can find out what the force of gravity is going to be. As it turns out, by the way, we would weigh about 40% as much on Mars. Again, that doesn't mean you're going to be able to jump 200 feet, I don't think. I think you might be able to jump, 12 feet if you're really talented. But you're not going to be able to jump the way that movie about the guy on Mars. You're not going to be able to jump that far. Anyway, we could stop there. If your brain is full, take a break. But there is one more little tidbit in this section of Young and Freedman's chapter, and they basically calculate the density of the Earth. Density is how much mass per volume. And so first they figure out what the volume of the Earth is. You may remember from some painful math class in the past, that the geometry, that the volume of a sphere, you figure out the volume of a sphere by, and volume is how much space is taken up, is 4/3 pi times the radius cubed. So we just substitute in the radius of the Earth into this formula, and ta-da! We find that the volume of the Earth is roughly 1 times 10 to the 21st power meters cubed. Okay, so now we figure what the density of the Earth is, where the Greek letter rho, it's not a P, it's a rho. The Greek letter rho, we basically mass per volume, right? We know the mass of the Earth now, we know the volume of the Earth. We just do a little simple division, simple for a change, and it comes out 5,500 kilograms per meter cube. That's the average, I should say, the average density of the Earth. As it turns out, and there's a lovely little map in color in this section, basically where we find out that the Earth is much denser at its core than at its surface. So the density of the Earth is not constant throughout it. It's much less on the surface than it is in its core, which makes sense. But anyway, so this is an average mass per volume for the Earth, not a precise one. Well, weight. This has been weight in section, which section is it? 10.2? Anyway, of Young and Freedman's University Physics. Weight.